Okay, so yesterday we were talking about Kepler, okay, and how Kepler had discovered how objects move in the sky, how they move in elliptical orbits, and they orbit the sun. At least we're talking about planets in our solar system, okay, things of that nature. Now, the thing we have to remember is that Kepler did all of this with no knowledge of the force of gravity. So today, we're going to talk about the force of gravity and how it basically confirms all of the things that he discovered and calculated. Now, the thing to know about this is that this is often referred to as Newton's universal law of gravitation. And that's just because, well, everybody figured Newton knew everything. When in actual fact, Newton never made the universal law of gravitation work. He came up with the idea, but never made it work properly. It actually took another scientist coming along later, named Cavendish, to actually design an experiment that could make his idea work. So he's still credited with it because it was his idea, okay? But somebody else made it work. All right, so that's what we'll be looking at here. So we're going to learn the relationship between gravitational attractive force, the force of gravity, okay, mass, and distance. Distance is not something we have associated with the force of gravity up until now. All right, we've always just said force of gravity is m times g and left it at that. That's all well and good, provided you're where? On Earth, where you know what little g is. Okay? But the reality is that little g changes all the time, even on Earth. Okay? Little g is not 9.81 everywhere. That's the average. In fact, it even says that on your formula sheet. Average gravitational acceleration, or something along those lines. Average acceleration due to gravity. Okay? It's not the true one because it actually changes. Here, where we live, it's actually about 9.83. Okay? It's actually a little higher than normal. Any ideas why?
We're higher up.
Actually, if we're higher up, it should be less. Because we're lower down. Actually, I know you're thinking, but we're like 1,100 meters above sea level. We're higher up. Yes, we are. But it's actually the distance to the center of the Earth that makes all the difference. Once again, we're higher up. We're farther from the center of the Earth, except we're not. The Earth is not perfectly round. It's not flat. That's crazy. With a capital K. That crazy. Earth's not flat. We know that because we have things orbiting the Earth all the time that prove and show us the Earth's not flat. Okay? But it's also not perfectly round. It's actually somewhat elliptical. It's not a football. Okay? It's not a basketball either. Okay? It's somewhere in between. So actually, if you are standing at sea level at the North Pole, you are closer to the center of the Earth than if you are standing at sea level at the equator, even though you're at sea level in both places. Okay? The Earth is actually quite a bit larger around the middle than it is over the top. In fact, if you were to stand on the top of Mount Everest, which is technically the highest point on Earth, you will weigh more there than you would weigh with your toes in the sand on the beach at sea level at the equator. Weird, but true. Okay? The Earth is actually that elliptical. Right? Alright, so here's some examples. If I am standing at sea level at the equator and I have a mass of 70 kilograms, my weight will be 684.6 newtons. If I go to the North Pole, it's 688.8 newtons. Sorry, 688.3 newtons. Okay? And heavier at the pole because the Earth is squished a little bit. Okay? And that's because of the way it formed. Okay? It spun very quickly when it was young, and it was also kind of molten when it was young. And so that created a centrifugal or a centrifugal effect that actually produced it wider at the equator than at the poles. You can see this on basically all the planets in the solar system, especially Saturn, which spins really, really fast. It is visibly flat, but you can actually see that it is flatter at the poles, okay, and wider at the equator. All right, if I'm in Chicago, okay, which is about halfway between the equator and the North Pole, okay, 686.2. So again, heavier, okay, than I am at sea level at the equator. Top of Mount Everest, 685.4. So I weigh more on the highest point on Earth than I do at the equator at sea level, because I'm closer to the center of the Earth here on the top of Mount Everest than I am if I'm at the equator at sea level. So, if you're looking at Olympic records, where are more records going to be broken? Near the equator, yes. Okay. Anytime the Olympics are held near the equator, more records are broken than they are if they are held further north. Because everything's just a little lighter there than they are further north. Okay? Statistically speaking, more records are broken when the Olympics are held near the equator than they are if they are held elsewhere. Okay? All right. If I go into low Earth orbit, so I'm on the International Space Station, I still have weight. Low Earth orbit, I still weigh 647 newtons. Why is everything floating around then? You're flying and dropping, exactly. You're only apparently weightless when you're on the International Space Station. You actually still have weight. If you didn't, you wouldn't orbit the Earth. You'd fly off. Okay? You're still attracted to the Earth. You're just moving fast enough that you're always falling and never getting closer to it. Okay? That's why you feel weightless, but actually aren't. Okay? If you're in high Earth orbit, where our geosynchronous satellites are, okay, our GPS ones, you only weigh 15.5 newtons. Why did it drop so much from here to here? Okay, but why did it drop so much? When I went from here to here, that was still a pretty big jump, but it only made a difference of 40 newtons. When I went from here to here, it made a difference of 600 and something, 630. The answer is that the formula for force of gravity is big G times mass 1 times mass 2 over r squared. So the farther away I get, I will feel exponentially less attraction to the other object. Okay? That makes sense to everybody. Now, this is where Mr. Dickey does this thing that makes everybody, including me, feel really uncomfortable. Okay? He makes everyone look at somebody else deep into their eyes and say, I'm attracted to you. And it makes everybody feel really awkward. So I'm not going to make you do that. Even though it's true, I'm not going to make you do that. Okay? Because you are, in fact, attracted gravitationally, okay, not romantically, okay, to everything around you. The problem is that there's one thing that's near you that you're way more attracted to than anything else. And that doesn't mean anything. Doesn't mean that your girlfriend or boyfriend or whatever means anything less. You're just way more attracted to the Earth than you are to anything else. Okay? Why are you more attracted to the Earth than anything else? It's huge. Okay? It's absolutely huge. And the force of gravity is dependent on the masses of the objects that are attracted to each other and how far apart they are. Okay? But the Earth is huge. So we don't notice the gravitational attraction to anything else. Okay? Standing on the Earth's surface, we can't attract a piece of dust floating in the air towards us by gravity. It's way more attracted to the Earth. Okay? We don't have enough mass, and neither does that little piece of dust, to make any difference in the path of that piece of dust. It's going to fall towards the Earth. Right? Even if I was in space, long way away from Earth, would I be able to attract that piece of dust toward me? No. Okay? Again, I'm way too small, okay, to have any real effect, gravitationally speaking, on something else. It does, however, mean that theoretically, if you continue to eat and eat and eat and eat, eventually food would come to you. If you got big enough. food would become gravitationally attracted to you, which would be good because by the time you were that big, you're not going toward it. Okay? You're not moving at all. Okay? Food would have to come to you, or you'd start losing weight, which actually might be a good thing if you were actually that big, because, well, you would make the Earth look like it had a growth, because you have to be that big, and you're not. So nobody can get that big. Theoretically, it would be possible. All right. Yeah, but it's true. Okay. So are you kind of understanding how this works? All right. So these are the things that can affect the force of gravity between two objects: the mass of the two objects and how far apart their centers are. Okay. All right. So Newton studied these attractive forces. This is the whole Newton got hit in the head with the apple stories. It's all crap, by the way. He just made it up. Okay. Newton made up a lot of things, actually. Okay? He was just so widely respected that people just took whatever he said for fact. Okay? But he made up this story about how he was sitting under a tree and his apple fell and hit him in the head. And the apple hit him because he got between it and the thing it was attracted to. What was it attracted to? The Earth. Okay. Now, he said that it was attracted to the Earth because both the apple and the Earth had a mutual attractive force between them. Not because the apple was attracted to the Earth, but because they were both attracted to each other. Also true. Seems strange because we see everything move towards the Earth. Okay? And it does. But technically, the Earth also moves. But because the Earth is so massive, you even notice it. Okay? But there is an attractive force that is mutual between two objects. It's easier to visualize if these are two big rocks in space, not near anything else. They're obviously attracted to each other, not one to the other. They're both attracted to each other, so they move towards each other. Okay? So the force of gravity is not a force that one thing exerts on another. That's kind of the way we've treated it up until now. But it's actually a mutual attractive force between two objects.
Is that how magnetic forces work?
Magnetic forces also work that way. Same with electrical forces. Okay, so if I've got a north magnet and a south magnet, they're equally attracted to each other. Okay, a positive charge and a negative charge are equally attracted to each other. There's a mutual attractive force between. It's never one on the other. Okay, but we visualize it that way because we see everything fall to the Earth. Okay, but in actual fact, they're equally attracted to each other. Okay, so it is important to understand that those forces are mutual. Okay, now, Newton came up with this idea, except his idea was missing one important thing, and that's this variable here. Okay, Newton understood that two masses would exert a mutual attractive force on each other based on how far apart they were, but he could never make the math work. Okay, according to the way he did it, everything should obliterate everything else because the forces would be incredibly massive. Okay? And so we couldn't make the math work. And the main reason he couldn't do that was because he could never remove the effect of the Earth's gravity from any of his experiments. Okay? Earth's gravity always interfered when he tried to measure the attractive force between two objects. He'd let them go, and what would they do? Fall to the Earth. Okay? Or if he put them on the ground, they'd just stay there because they were attracted to the Earth. They wouldn't move towards each other. He couldn't figure out a way to measure the attractive force between two things that were very small without the Earth's gravity getting in the way. Okay? He was right about this idea, okay, that their mass was important, that how far apart they were was important, but he couldn't make it work. Okay? It took another person coming along to design an experiment that removed Earth's gravity from the experiment. Okay? And that person was Cavendish. Right? So Cavendish designed an experiment like this. Okay? What he built is what's called a torsion balance. Okay? So what he had was he had a pole, okay? And on this pole sat this bar with a big lead sphere on each side. Okay? And this thing could pivot on the bar. Okay? So he sat it on this pole, okay, and he had it sitting there. Then he had a torsion fiber. Now, the torsion fiber is like a thin cable. Okay? And he knew the tensile strength of this cable. That is, he knew how much force would be required to twist it a certain number of degrees. Okay? So he hung on this cable a mirror and two spheres that were made of like pith, kind of like styrofoam, really lightweight stuff. Okay? So he had those on the end of that. And he set it up like this so that these things were close to each other. Now, which way does gravity act? Down. Which way is the force of attraction between these? sideways. Okay, so now gravity had no components within the plane that these two things were attracting each other. They were horizontal, and they weren't touching the Earth, so the Earth's gravity couldn't affect them. Okay, so here's what happened. He placed this thing in this position and let it go, and the balance started to twist. Okay, so he had a beam of light coming towards this mirror. Before he let it go, the beam of light just reflected straight back on itself. But as soon as he let the apparatus go, there was a torquing force because of gravity that twisted the cable and turned the mirror X number of degrees. Okay? From that change in angle, he was able to calculate how much torsional force was being applied to the string. And that torsional force was being caused by gravity. Okay? The gravitational attraction between these two objects. So he was actually able to measure a force of gravity that wasn't being caused by the Earth. And so as a result, he was able to calculate the one thing that Newton always was missing. Okay? He knew the mass of the pith ball, he knew the mass of the lead ball, he knew how far apart they were. Okay? Since he knew all of those things, he was able to calculate big G, which is the gravitational constant of the universe. At least this other universes, if they exist, might have different gravitational constants we don't know. Okay? All right. So now, thanks to Cavendish, we have a working formula that allows us to calculate the force of gravity between any two objects based on their masses and how far apart they are. This formula is crucial to space travel. Okay? If we're going to send like a spacecraft to Mars or to Neptune or wherever, okay, we need to know how it's going to be affected by the things it passes. In fact, we often use gravity as a propellant. Okay? Some people have seen The Martian. Okay? Several times in The Martian, they talk about a gravity assist or a gravity slingshot. Okay? The gravity assist maneuver makes a spacecraft fly towards something else, accelerate due to gravity, and then veer off at the last minute in order to gain some speed without having to use any propellant. Right? So that's dependent on this. So the people at NASA are basically using that formula to figure out how much gravitational force will be exerted on a spacecraft, how much velocity they can gain from that, and how much faster they can make the spacecraft go. Okay. All right. Everybody all right with that? Now, the other thing we need to understand is that there is this exponential or inversely exponential relationship between distance and the force of gravity. Okay, so remember, force of gravity equals big G times mass 1 times mass 2 over r squared. So as r gets bigger, Fg gets exponentially smaller. Okay, so if I double the distance between two objects, the force of gravity between them will be 4 times smaller, or 1/4 of what it was in the beginning. Okay, so it decreases very, very rapidly as you move away from an object. Okay, now, Cavendish, his number, the universal gravitational constant, is on your formula sheet. You will be using it a lot over the next week and a half or so. Okay, it is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. You don't have to remember the units. Okay, in fact, you don't have to remember the number because it's on your formula sheet, but you're going to be using it all the time. Okay, that's the number that now makes all of our forces work out. Okay, in terms of we get them nice and small like they're supposed to be, as opposed to these, crushing numbers that Newton was getting. All right. So let's have a look at this example here. Let's say that astronauts take like a cantaloupe or a honeydew or something to the moon with them. Okay, and we want to figure out what its weight on the moon will be. Now, we could go m times g, but that would require us to know what? We have to know what g on the moon is. And I don't know what that is off the top of my head. I think it's like 1.6 something, but I don't know for sure. Okay? If I can't use that, then I'm going to use this. Newton's universal law of gravitation will allow me to calculate the force of gravity between the melon and the moon, in other words, the weight of the melon on the moon, if I know how far from the center of the moon it is, which they tell me right here, and the mass of both the melon and the moon. Well, here's the mass of the moon, and there's the mass of the melon. So I can do that. I can do it this way. Right? So I'm just going to plug in my numbers here. 6.67 times 10 to the minus 11 times 0.65 kilograms, mass of the melon, times 7.36 times 10 to the 22. That's the mass of the moon in kilograms. Divided by the radius of the moon. Why am I using the radius of the moon? Right, that's how far from the center of the melon to the center of the moon it is, and that's the number I need. It's the separation distance. Okay, and that number is 1.74 times 10 to the 6 meters, and it has to be squared. You'd be surprised how often people forget that. Then they also get a ridiculous number and don't realize that it's a ridiculous number. All right, so if I do that, it's going to be a little bit hairy plugging that into your calculator. You got to use a lot of brackets. So 6.67 times 10 to the minus 11 times 0.65 times 7.36 to the 22 divided by 1.74 6 squared. Whoops. Squared. All right. So the melon has a weight of 1.1 newtons on the moon. Okay? They follow how that formula works. Okay? I mean, you might have to manipulate that formula, solve for one of the masses, or solve for R. Okay? So it's not a terribly hard formula to use. All right, so that's what we just did there. Okay, now, gravity can obviously act as a centripetal force. Okay, we see that all the time because the moon orbits the Earth orbits the sun, and so on and so on. Gravity acts as a centripetal force. I think they could put it off, sit up, or I'm going to throw something. Okay, so gravity can act as a centripetal force. Okay? And it does it in this way. It makes things move in a circle because without gravity, things would move in a straight line according to Newton's first law. However, they are attracted to other masses, so they move towards each other. But they're still moving very fast, but they're attracted to other things. But they still move very fast, but they're attracted to other things. I don't have to keep saying that, do I? Okay. If I take all of these vectors together, I get it. Okay. Gravity acts as a centripetal force for orbiting objects because it's a combination of their inertia, how fast they're moving, and the force of gravity pulling them towards the center. Okay? In the same way that when I whirl something around and around in a circle using a string, the string pulls it back, but its inertia wants it to go straight. Okay? It works exactly the same way. Now, in space, if we're talking about the moon, we saw yesterday that it's not just the moon, okay, and the Earth, it's also the fact that the Earth changes shape a little bit, the moon changes shape a little bit, and that's why the moon's going a little further away all the time. Okay, but again, that's all kind of part and parcel with what's going on here. Okay, so if there's no gravity, it's what we just explained. The object moves in a straight line, okay, like this, and then it's attracted to it, so it moves towards it. So that's just the explanation of what I just said. Okay, so gravitational force is a centripetal force. So Fg equals Fc. Up until now, we've written that like this. But if I don't know what little g is, can I substitute in the other formula for the force of gravity? Yes, I can. Okay. I can substitute in and say that big G times mass 1 times mass 2 over r squared equals mv squared over r. Gravity can act as a centripetal force, okay? Even if I have to calculate it that way. All right. So if I'm saying this and this, would this also be true? Right? It would be, right? It would have to be true. Okay, now, I've got a mass over here, I've got two masses over here. If I start manipulating things around, okay, which mass would cancel? The big one or the small one? Okay, why would the small one cancel? Are all things affected by gravity in the same way? Yes. All things accelerate at the same rate. Okay, so if I'm solving for, like for example, if I'm solving for little g, the small mass would cancel because little g is based on the bigger object's gravitational field. Okay, I'd be able to solve for that. Okay, we'll get to that another day. Right now, let's see if we can calculate how fast the moon moves in its orbit based on this idea that gravity can act as a centripetal force. Okay? So, we're going to say that Fc equals Fg, okay? And we're doing this for the moon. So we're going to say I want to figure out how fast the moon is moving in its orbit. What am I solving for here? V. Okay? Okay, so I want to get V by itself. I'm going to multiply both sides by R. What happens to the R's? Okay, so the squared goes away and this R goes away. All right, I divide both sides by the mass of the moon. It cancels out. All right. So, hold on. What is that? If the mass of the moon cancels, does it matter whether I have a moon out there or a garbage truck or a basketball? Or they all have to move at the same rate? Yeah, if the mass cancels, then actually mass doesn't matter for something. The only thing that determines how fast you have to move in orbit is how far apart you are. Okay? Because again, all things fall at the same rate. All right, so now I need to square root. That'll give me V. All right, so the speed of the moon in its orbit around the Earth is going to be 6.67 times 10 to the minus 11, big G, multiplied by the mass of the Earth, 5.98 times 10 to the 24 kilograms, that's on your formula sheet under other usable constants, okay, divided by what? What distance do I need here? From the center of the Earth to the center of the moon. On your formula sheet, that is written as average Earth-Moon distance, and it is 3.85 times 10 to the 8. Okay? All right, so calculate how fast the moon's got to move in its orbit. Again, this can get pretty hairy in terms of your data entry into your calculator. I wouldn't recommend trying to do this all in one step on your calculator. I do it a bit at a time. Okay, so I'm just going to do the top part here first. So I'm going to go 6.67 e negative 11 times the mass of the Earth. I don't know why I did two brackets on that. Okay, so there's the top. Now I'm going to divide that by the bottom. And then I'm going to square root it. Okay, so the moon moves at about 1 kilometer per second. Okay, 1,017 meters per second is how fast the moon needs to move in its orbit in order to not fall into the Earth. Because if it moved any slower than that, it would get closer and closer to the Earth. Okay? Since it's actually going slightly faster than that, it's actually getting further and further away by 2 centimeters a year. Everybody follow what we did there? Okay, so that is the principle behind all satellite motion, which is what we're going to talk about tomorrow. Okay? Today we're just looking at force of gravity for the sake of itself. All right, now we were talking here about if we're sending a spacecraft out into space. Okay, so if we're sending a spacecraft out into space, it obviously is going to not just go to usually one place. Okay, it's going to use what we call the gravity assist method in order to gain speed and use less propellant and things like that. So you can see that missions that start from Earth will often go to other places on their way elsewhere. Okay, so if we're looking at any of these deep space missions that we've sent out, the Voyager probes and things like that, Pioneer and stuff, we send them out, they go to one planet and they slingshot around it. Okay, then they go to the next planet, they slingshot around it, and they head to the next one, slingshot around it, and out to the next one. Okay, so they're constantly using that gravity assist method. Okay, that's basically just using the same formula we just used. Okay, that's using that formula allows the rocket scientists at JPL to figure out how fast they can get something going, what direction they need to aim it in, all of that kind of stuff in order to get something where it's going. Okay, it's a lot more difficult than we make it sound when we talk about it that way. Okay, they have to do a lot of calculating. Even a small calculation error means you miss an entire planet by so much you get nothing out of the mission. Okay, so that's bad. Now, is it difficult to make this happen effectively all the time? It is. Okay. In fact, if you look at this diagram, there's a color coding to this diagram. Okay, so you can see that there's some bright colored lines and then there's some dim colored lines in between them. The bright colored lines represent successful missions. The dim colored lines represent failures. Okay, so our closest neighbor, the moon, has been visited the most, but there's a lot of dark lines in amongst those bright lines. There's more bright lines than dark lines. We're reasonably successful at sending things to the moon and either getting them back safely or landing them there or whatever, because it's not as far. Okay? Sending things to Venus is a bit more interesting. Okay? It's a little bit further away. It's towards the sun. Okay? And Venus itself is a very inhospitable place. Okay? Now, the Russians did the majority of the exploration of Venus. Okay? They sent like tons and tons of probes. They're called the Venera probes. The first one they sent just orbited, and it took pictures of Venus. Did a good job. Then they decided that wasn't good enough. They wanted to try and get something into Venus's atmosphere and eventually down to its surface. Okay? What's the problem with that? Well, no, there's a surface on Venus.
It's really hot on Venus.
It's super hot on Venus. And not only is it super hot, but Venus's atmosphere is 100 times thicker than Earth's. Okay? So imagine feeling 100 times the atmospheric pressure you feel right now. It's actually like being at the bottom of the ocean on Earth. There's that much pressure. Like it would crush a nuclear submarine. Okay? The force of the atmosphere. Okay? In fact, the atmosphere is so dense that at the surface, it's more like a liquid. Okay? So imagine walking through air that was like water. Okay? That's what it would be like to try and move around on the surface of Venus. In addition to the fact that it's hotter than your oven on the self-cleaning cycle. Okay? So like 500 degrees Celsius or more, okay, in a lot of places on the surface. So like super nasty, really, really hot. Okay? So the Russians, they send the first probe, okay, or the second probe, and it gets only a few kilometers into the atmosphere before it's crushed like popcorn. Okay? So, the Russians are like, okay, we make a mistake. We go now, we make bigger, stronger thing, and we send it there. Okay? So they just basically reinforce this thing, and they keep sending these probes. They keep reinforcing them. They get better and better, but there's a lot of failures because there's a lot of times where the atmosphere just crushes the thing. Okay? In addition to the fact you have to worry about it burning up. Okay? Anytime you re-enter an atmosphere, you can burn up. Well, when the atmosphere is 100 times thicker, that problem's 100 times worse. Okay? So they basically had to build something that on Earth would be basically indestructible. Okay? So eventually they get one that can actually successfully land on the surface of Venus. And they're like triumphant. They're now ready to take a picture of the surface of Venus and a sample of its surface. So they've got this little robotic arm that's right below the camera. Okay? And the robotic arm is just going to go like this, lay down, and it's going to touch the surface, and it's got some sensors on it that will tell it what the surface is made of. Okay? So, first, we want to take a picture. Now, you don't send a camera to the surface of Venus without a cover. So there's a little pyro, a little explosive thing that pops the lens cap off. So it takes the lens cap off, takes a picture of the surface of Venus, then the sampling arm goes down. What does it sample? The lens cap. The only thing brought to the planet from somewhere else. And they go, oh, the surface of Venus is made of, hey, isn't that what their spacecraft's made out of? Oh, you can bet somebody ended up in salt mine in Siberia for some design flaw. Okay? So they ended up sending a bunch of probes after that. They got samples, they got good pictures and things like that. Okay? So you can see there were a lot of dark lines here, okay, in the initial going. Right? Now, Mars, similar problem. Landing on Mars is really difficult. Only about slightly less than 2/3 of missions we send to Mars are successful. Because Mars has the opposite problem. Its atmosphere is 100 times less dense than Earth's. Still thick enough that things can burn up in the atmosphere if they don't go right, but not thick enough that we can slow them down really well. Okay? So we have to have all these different mechanisms for slowing the spacecraft down and then landing it gently on the surface so it doesn't just become a crater. There's a number of those on Mars from us. Okay? A lot of failed missions just ended up as a smoking hole. Okay? But yeah, it's really difficult to do that, and there's been a whole bunch of different methods like the balloons and the big parachutes, and so the airbag method. So basically, just before the spacecraft lands, all these airbags inflate, and then it bounces along on the surface until it stops, and then they deflate the airbags, and the little rover can drive. Okay, so Curiosity and Spirit both landed. Sorry, Spirit and Opportunity both landed that way. Okay, and their latest one, the Curiosity rover, which is the size of a golf cart, okay, was landed using the Sky Crane, which is this ring of rocket engines. So the thing descends a little ways by parachute, and then these rocket engines engage and lower and hold the spacecraft kind of just above the surface while this crane lowers it down. Okay? Right before the thing is lowered to the surface, the cable is severed. Okay? Now, why do they want to sever the cable and not just lower it all the way down? No, the rocket engines would burn the spacecraft. Okay? So, when it's about 10 meters above the surface, they sever the cable and it falls the last 10 meters to the surface. Now, on Earth, falling 10 meters is a big deal. Why isn't it a big deal on Mars? Right, it's only falling 3 meters. Okay? It's only like falling 3 meters on Earth. Okay? So the thing kind of lands roughly, but safely. And then the rockets just fly off and crash. Okay? But they fall off and they crash somewhere else, and they don't wreck the spacecraft. That was their big worry, was that they would scorch the spacecraft or do something else to it. Okay? So they had to lower it. They had to let it go in a different place. Okay? They were really worried about that. The problem with that is they can't do that remotely. They can't have a guy sitting at a computer, okay, operating the spacecraft and lowering this thing down. It has to all be done autonomously by the spacecraft. Why? Yeah. The delay between Earth and Mars can be anywhere between 20 minutes and over an hour. So you can't be going, okay, shift it to the right a little bit, and then wait an hour to see if it shifted to the right. Actually, it's like wait 2 hours. You got to wait for it to get there, wait for it to happen, and send a response. Okay, so you can't do that. That all had to be done by the computer on board. So they were really worried. Okay, there was a point where in the landing they're like, okay, now it's all hands off. It's either a smoking crater or it's sitting on the surface and it's good. We're not going to know for another 19 minutes. You can imagine your whole life's work. And you're waiting 19 minutes to find out whether it's still there. Okay, so we use all these things here, all these gravity assists that gets us out to the far reaches. Okay, and we've got now several spacecraft that are out beyond Pluto. Okay, thanks to all these gravity assists. All right, so we did that already. Okay, I want you guys to try this question here. So we got Mount Logan in Yukon is 5,959 meters above sea level. It's the highest peak in Canada. Okay, Earth's mass, they're saying it's a slightly different number. We'll use their number for this question. Okay, it's 5.97 times 10 to the 24 kilograms. And its equatorial radius is 6.38. Again, slightly different than the one we have, times 10 to the 6 meters. What would be the difference in magnitude of the weight of a 55 kilogram person on the top of the mountain compared to at sea level? Okay, so you got two calculations there. I want you to see if you can figure out how much more or less they weigh on top of the mountain than they do at sea level. All right, give you a couple minutes on that one. Okay, so what we have to do with this one is we just need to figure out what the person's weight is at sea level and then what their weight is on the top of the mountain. Okay? The only thing that changes is our radius. So if we go Fg at sea level, okay, that's going to be 6.67 times 10 to the minus 11 times 55, their mass, times 5.97 times 10 to the 24. And that's going to be divided by 6.38 times 10 to the 6 all squared. Okay? When we're talking about the force of gravity on the top of Mount Logan, okay, then all we do is change the radius. So we're still going to have these same numbers, 10 to the minus 11, 55, and 5.97 times 10 to the 24. But what's going to change is now this number, 6.38 times 10 to the 6, will be added, or will add on, sorry, the height of Mount Logan. And squared. Okay? That's the only thing that's different between the two. They should be lighter on the top of Mount Logan because they're further away from the center of the Earth. Everyone kind of follow me there? Okay. Now, in actual fact, that's not true. Standing on the top of Mount Logan, you'd actually be heavier than you would be at sea level at the equator. Okay. This doesn't say anything about it being at the equator. It just says assume equatorial radius. Okay. So if we do that, we're going to find that it's like less than a Newton or around 1 Newton. Yeah. Okay. So if we punch it in, okay, so our first one here will be sorry, they've got 6.38, right? Okay, so at the equator, or at the equatorial radius, the weight's going to be 538 newtons. Okay, the only thing I change now is that in here, okay, I'm just going to add in an extra bracket here so I can put in the plus part. So plus 5959. End bracket and square it. Okay, so on the top of Mount Logan, it's 537 newtons. So it's 1 Newton difference. Are you even going to notice that? 1 Newton out of 530 some, you're never going to notice that. Okay, it's like 0.25% of your weight. It's ridiculously small. Okay. In actual fact, you would be lighter on the top of Mount Logan because of the extreme energy demands in getting there. You would actually lose a lot of mass in climbing that mountain. Okay, you burn a lot of fat, use up a lot of muscle and stuff like that. In getting to the top of Mount Logan, people tend to lose a lot of their body mass in making a climb like that.
So would this formula work like inside a black hole?
Yes. Technically, it can work anywhere where two objects are gravitationally attracted to each other. Okay, so if we're talking about an object this far from the event horizon of a black hole, that number would be huge, but yeah, it would be calculable. Okay, so I want you guys to try these two. Okay, they're just like what we just did there. They're just using the force of gravity formula. Okay, finding the force of gravity between two people sitting on a park bench. It's going to be pretty small. And then the force of gravity between the Titanic and the iceberg that sunk her. Also going to be actually quite small. Okay, but because it wasn't because of gravity, it was because the captain was drunk and the navigator was blinded. Okay? Yeah, it was dark. You didn't see an iceberg coming until it was too late. Okay, so for number 1, okay, remember, force of gravity equals big G times the mass of 1 times the mass of 2 over r squared. Okay, so we'd have 6.67 times 10 to the minus 11, okay, multiplied by the mass of each of the people, so 55 and 80, and then divided by the radius between them, and here's the part people forget, that's squared. If you forget to square it, you're not going to get the right answer. If you do remember to square it, then you should get 8.2 times 10 to the minus 7 newtons. Okay? Certainly an incredibly small force that would not result in you sliding towards each other on the park bench. Okay? So you're not going to feel any gravitational attraction to that. Okay? Right. We'll talk some more about satellite motion and gravity tomorrow.
So